Okay, so my name is BJ Dweck. I've been in the space for a while. I've been building here in the space for a while, and over the years, people have approached me, and as newcomers come into the space, I usually receive the same set of questions, and and also a bit of confusion about what this is, what was done here, and if you look around, there's no shortage of articles in the mainstream media about Bitcoin, about crypto, about blockchain. Um, but you get the sense when you read articles that perhaps the author can't really give you a coherent explanation of what this is and what was done. And I think that there's really a lack of that. And I built this presentation to perhaps try to fill that void, and give an Eli 5 explainer to what Bitcoin is, what technically was done, um, and very very agnostic as to value propositions, and you're not going to see any charts or graphs here. This is just a purely technical explanation of what was done here in 2009, what happened that enabled this this explosion of this whole industry that you're seeing. And before I begin, I also want to just make a shout out and thank the following people: Matt Odell and Giacomo Zucco, 6102, Zender goes by Zentoshi on Twitter, um, and Armin the Parman, Hodlwave, who gave such thoughtful feedback to my presentation. So yeah, thank you very much for giving the time to listen to a presentation by some random guy on Twitter. Um, and thank you very much for your thoughtful feedback. So to jump right in, I'm going to give a little bit of context, and I'm going to explain that there are two models generally of communication on the internet. There's a centralized model and a decentralized model. And it looks something like this. So, the internet affords us with this infrastructure. We're all a bunch of computers connected by these pipes, and the information travels much like the mail system. It's forwarded in little packets, little envelopes with addresses on it, and we all have IP addresses on the internet. Now, the servers that we contact have IP addresses. We have IP addresses. They're really no different. And there are routers on the internet that route these envelopes, these packets. And the question is, how do we layer on top of this an application, right? How do we all the things that we do every day on the internet, banking and Facebook and Twitter, and how does this work with this basic underlying infrastructure, this base layer underneath it? And so we generally use something called a client-server model, which is a centralized model of communication. And the way that this works is we have some server out there that has an IP address. Again, just like you have an IP address, I have an IP address, and this computer is, theoretically no different than your computer or mine. Perhaps it has more computing resources because it has to do a lot, but it doesn't have to be different hardware-wise. And it has a database. It has some kind of repository for data that perhaps we're interested in retrieving or altering in some way, right? If we have accounts at Citibank, perhaps we're interested in checking our balance. And so we obtain the server's IP address by looking it up using their domain name, and then we send a request from our computer to this server, and then the server completes our request. Perhaps it feeds us with information that we requested, or perhaps balance is moved from one account to another, and that's the way that we use all of our applications today. 99% of what we do on the internet works this way. So what's the alternative to this? What could we, contrast it with this model here, called a decentralized or a peer-to-peer model. The only application really that's taken advantage of this largely to this date is the BitTorrent protocol used for file sharing, and it works something like this. All right, so say that several computers out there, several nodes, several individuals have copies of a movie, The Matrix, right? And so someone is interested in sharing that file. Let's say Bob comes along. He wants a copy of this file. So Bob just has to obtain the IP address of one of these participants, one of these nodes on the network, one of these computers on the network. Let's say Alice, Dan, Charlie, Evan. And then they can forward him a list of all the other participants' IP addresses. And then he can connect to them individually and request bits and pieces of this file of the matrix. And then collectively, they'll send those bits and pieces to Bob. And now Bob has a copy of the matrix on his end, and notice that he's now a fully fledged member of this network, right? Which is sort of interesting, right? So if Fred, for example, wanted a copy of this movie, now he could reach out to Bob, and he could get a list of the IP addresses of all the other participants, and he can retrieve the movie in much the same way. Now, what's interesting about this model is that there is no central server that we're dependent on, right? This makes this model very resilient to attack, right? We often see that sometimes servers are hacked, sometimes they are brought down, and when they're compromised and brought down, so the service is compromised and brought down for the entire list of clients, the entire customer base of that server, right? And the service is then unavailable, right? So what's interesting about this decentralized model is it's highly available, right? Because if the United States, for example, manages to take down all of the nodes in the United States, Charlie and Evan, well, Dan, Alice, and Bob are still online, and so the service is still available, right? What's also interesting about this model is that everyone is a peer, right? It's very difficult to distinguish between the peers on this network, we call them. So this is called the decentralized model. And the story that I'm going to tell you today, the story of the creation of Bitcoin, is the story of replacing what I call the centralized books model with a decentralized books model, right? So first, let's understand what is a centralized books model. Well, what we're going to do is we're going to consider a bank, an online bank, a server here, Citibank, and we're going to consider intra-bank transfers, right? That is, transfers of balance between two account holders at Citibank, right? What we're not going to consider are balances external to Citibank, right? To and from places outside of Citibank, right? We're just going to consider intra-bank transfers, right? And if you think about it, right, all of the data for all of the account holders in this intra-bank Citibank scheme set of books, it can be maintained as sort of an Excel spreadsheet, right? You can think of Citibank as holding this Excel spreadsheet with just 3 columns in it, right? A from account, a to account, and the units, right? And as participants in this bank, in this private bank, are sending units to one another, right? We can just append transactions to this log, right? You can think of this Excel spreadsheet as a transaction log, right? And by rewinding to the beginning of the log and playing it through, you can then tally up the balances of all of the holders of accounts on this log, right? Alice sends Bob 50 units, Charlie sends Alice 10 units, etc., right? And so the problem that we're going to solve today is, let's say we wanted to maintain a log like this, an a private bank for some reason. Say that we all, we're all co-workers, we buy each other lunch every day, and we want to keep track of this, right? So naturally the question arises, well, who holds this Excel spreadsheet, right? And do we trust them? Yeah, sure, we trust them. We're all a bunch of co-workers, right? Well, let's say we wanted to extend this to strangers, right? It would seem that that would be a very difficult thing to do, right? So the problem that we're trying to solve today is how we can turn that centralized books model into a decentralized books model, right? And we can see almost immediately, right? Perhaps the question itself sounds very strange because you can't imagine how we could do something like that, right? Again, we're putting aside the question of why we would want to do something like that, right? We can visit that later after we discuss how we could do something like that, right? Because it's very difficult on its face, right? It would seem if Charlie wanted to steal money, if Alice rather wanted to steal money from Charlie, all that she would have to do is draft this transaction from Charlie to Alice, 40 units, and she could just append it to her copy of the data, right? And as we saw on that decentralized slide, right, that that transaction, right, would just propagate across the network and would be appended to everyone's log, right? And she will effectively have stolen money from Charlie, right? And so that can't work because this is an environment of no trust, right? We're not a bunch of coworkers who trust each other. We're a bunch of strangers on the internet, right? And it's perhaps even worse than that, right? We don't, we're trained not to trust data that comes in from some source on the internet, to be suspicious of it with good reason, right? There are hackers that are, looking to take advantage of us. And so perhaps that's why really the only protocol that took off in a decentralized sort of model is BitTorrent, because when you're sharing a file, right, perhaps the cost is very low, right? If I reach out and I try to get a copy of the matrix and it winds up not being the matrix, right, I really didn't lose very much, right? But if I'm doing anything else, if I'm getting sports scores, if I'm doing balance transfers, right, I need that trust, right? And so I need that server, right? I need to be dependent on the fact that I trust this server, right? That's a lot of responsibility to be giving the server. I'd like to ideally do away with it, but it would seem that there's no way to do this, right? And so that is the story that I'm going to tell today, how we can replace the centralized books model with the decentralized books model. And that is what Satoshi Nakamoto, the pseudonymous creator, drafter of the Bitcoin white paper, he came up with a solution on how to do this, how to replace that trust with the ability to verify everything that comes in, so that you don't have to trust and take at face value these transactions. You can verify that they're authorized, that they have sufficient balance, and that they're coming in at the right order. And so we can all have transaction logs that are in sync. Note, by the way, this is just an image. We don't actually know who Satoshi Nakamoto is. He remains anonymous to this day. So if we think about it, right, there are three problems that we need to solve in order to come from the centralized books model to the decentralized books model, right? The first is around transaction authorization, as we saw, and we'll see again. The second is around coming to a consensus on transaction ordering. In other words, it's not enough that we have the same transactions in our logs in this peer-to-peer network, right? We have to have the same transactions in the same order, and I'll illustrate why that's important in a moment, right? And number three is around the creation of units of account, right? Because you might be thinking, okay, this idea of this transaction log is very interesting. Well, what if I rewind to the first transaction where Charlie sent Alice 40 units? Right? Well, where did Charlie get those 40 units from? Right? So it becomes very clear that we need some mechanism, some method for the creation of units of account on our transaction log, on our ledger, right? Our set of decentralized books. All right, so let's examine problem number one. So problem number one, just to reiterate, it's very easy for Alice to steal money from Charlie just by drafting a transaction that Charlie sent her 40 units and sending it to her nearest neighbor on this network, who, if we're just taking these things at face value, just going to add it to their books, and right away our decentralized set of books falls apart. So we may not even waste the time with this. Why should we attempt to do this? All right, so we're going to take a timeout and we're going to introduce two technical concepts, right? One is called a hash function, and the second is public key cryptography, right? And obviously this is an Eli 5. I'm taking some shortcuts here. If there are any cryptographers that are watching now, I understand very well how this works. Anyone looking for a good walkthrough of the actual mathematics behind it, I'd refer you to Jimmy Song's excellent book, Programming Bitcoin, for the details on that. But this is obviously a simplification. I found this to be the most effective way to bring newcomers into the space. So the first concept here is a hash function. Okay, so what is a hash function? Well, what is a function, right? A function takes inputs and gives me outputs, right? Any function maps inputs to output, right? Addition is a function. It takes two inputs. It gives me an output. And a hash function, right? A hash comes from hash browns. I'm going to scramble the input, right? It takes a single input, gives me an output that is simply scrambled, right? So that sounds a bit strange, right? If I give you a challenge, build me a hash function, you can come up with all sorts of crazy methods to do that, right? Take the first 60 digits of, the first 40 prime numbers and just add them to whatever input, and you'll get something scrambled, right? There are several hash functions out there, but they all have to obey the following criteria to be a proper theoretical hash function according to what we need in computer science, and they are the following. So for the same input, I have to get the same output every time, right? There's nothing special about that. That's just a corollary of being a function, right? A function gives me the same output for whatever inputs I feed it, right? Because it's just a procedure. The second criteria is the output has to be uniform and unpredictable. Okay, so what does this mean? It means that if I throw in some data, right, into this hash function, because anything in a computer, at the end of the day, we use computers that are digital, and all data is represented as numbers, right? So any piece of data can be an input to this hash function, right? You can even take the entire data set of Wikipedia, for example, and think of it as one tremendous number, right? Tremendously long number, and you can throw it into this hash function, right? So if I take a piece of data, let's say, a movie, a picture, let's say it's a book, it's a work of Ernest Hemingway, and I throw it in, and I get some number. If I take that same book, that same text, and I turn to page 57, and I change a lowercase m to a lowercase n, and I throw it in again, I'm not going to get the same number plus 2, right? I'm going to get a totally different number. I have an equal probability of getting any number on the output of this hash function. And incidentally, the hash function that we're talking about here is called SHA-256. It was developed by the NSA. And this particular hash function spits out a number that is on the order of 10 to the 77, right? That means that it's a 77-digit number, right? So take a second to think about what 10 to the 77 is. It's on the order of the number of atoms that there are in the universe. Right? That's a very, very large number, right? And so this hash function, it takes its input, it scrambles it, and I don't know what I'm going to get on the output until I actually run it. And I have an equal probability, right, if the designers of this function really did their job well, and they did some good scrambling, right? So I have an equal probability of getting any number on this output range. And even if I change that input by one tiny, tiny bit, still doesn't matter. There's no relationship, and I can't tell what I'm going to get until I actually run it through, and I have an equal probability of getting any output on the other side. Third criteria is that I never get the same output for two different inputs. All right, so now the astute listener is going to say to me, but wait a minute, BJ, you just told me that I'm getting an output on the order of 10 to the 77. That's a very large number, but it's still bounded, right? It's finite, right? From 0 to 10 to the 77. But you told me that I could throw anything in, right? I could throw infinity in, right? Very large numbers, 10 to the 80, right? 10 to the 1,000 into here, right? Right? How is it that for every single input, I'm going to get a unique output? That's impossible, right? So that's why I put never in quotes, because in practice, right, theoretically that is impossible. But this number is so large that the odds of finding two different things in our real world, two pieces of data that I could throw into this hash function and getting the same number twice is on the order of winning the lottery, right, 55 times in a row, right? So I can pretty much, bet my life that we can throw something into this hash function, two things into this hash function, we'll never get the same. We'll never get what we call a hash collision, right? And all of modern cryptography relies on this right now. All right. So the fourth criteria is that this is one way. It's irreversible, meaning I can't take the output here and run it backwards. Now, again, you might say to me, wait a minute, you just told me SHA-256 was developed by the NSA. You can look it up on Wikipedia. You can see the exact procedure that they use to get from an input to an output. Why can't I just run it backwards? So I'll say to you, well, there are some operations that are one way, right? They're irreversible. You can't run them backwards. For example, let's say I told you, pick a 20-digit number and add the last 10 digits to the first 10 digits, right? And then give the sum to your friend, right? And ask your friend, what was my original 20-digit number? So he's not going to be able to tell you, right? But wait a minute, he knows the exact procedure you used. You could tell him, all I did was add the last 10 digits to the first 10 digits, right? But it doesn't matter, right? Because there are too many different possibilities. And so the hash function uses many such operations many, many times. And so it's a one-way function. It's irreversible. Right. So now I just want to take a moment. I want to tie that down because I know it's very abstract. Why would you need something like this? And I want to give you just some context as to why we have a function like this in computer science by giving you some applications. So one potential application is we use this for digital fingerprinting for file synchronization. Right. If you think about it, a hash of a piece of data, a movie, a picture, it's sort of like a fingerprint for that piece of data because it's unique, right? And so we can use this, in all sorts of clever schemes. Like if I have an enormous piece of data, on one side of the world, in Asia, and I'm looking to sync it up with that same set of data in the United States. But I want to conserve on bandwidth, right? I don't want to needlessly send data to the other side of the world, unless I really need to synchronize them. So how can I tell when they fall out of sync, right? So one thing I can do is in Asia, I could take the hash, right? And in the United States, I could take the hash. And then I can just compare those two numbers. And I know that if the numbers are identical, so the data sets must be identical because no two things could hash to the same number. Right? Those are digital fingerprints. And as soon as one of the data sets changes by even the slightest amount, right, 1 bit, right, the smallest amount, it'll completely change the hash. You'll get a completely different hash. Another scheme is, this is typically used for password storage in databases. Because often, right, if you have a website and you want to register users, you want to be able to authenticate your users, right? So, you're very familiar with the username password scheme that we use, right? A user registers, John Doe, enters a password, perhaps Apple. But, if as a website, right, as a purveyor of a service, you're exposed if you maintain a list of usernames and passwords, right? Because a hacker could come, steal that database, and then use those usernames and passwords in other websites, right? And your users would blame you. They'd say, this is your fault. You didn't maintain my data well, and so you're exposed, right? So it's very uncomfortable to maintain a list of usernames and passwords, customer data on your website. But what's the alternative, right? So here's a potential solution to this problem: is that when John Doe registers with his username John Doe and his password Apple, so rather than storing Apple in your database, you hash whatever he typed in and you store the hash in your database, right? The next time he logs in, types John Doe, and he types something, and whatever that something is, you hash it, and you see if the hash matches the one in your database. He typed in the same thing. And if a hacker makes off with a list of usernames and hashes, well, it doesn't really do much good, right? Because you can't use the hashes to log in because you're just going to hash the hash, right? And you can't really use them in other websites. So, that makes things very difficult for a hacker. And this is a scheme that's typically used. Incidentally, that's often why if you forget your password, the site can't tell you what your password was. They can help you reset it, but often they don't or shouldn't know your password. All right, so that was the first scheme, first technical concept, hash function. The second is public key cryptography. So how does this work? It starts with a number, 77-digit number. There's nothing magical about this. I picked it at random, right? Maybe that is magical. It's usually difficult to pick a random number, especially if you're a computer. But it starts with a random number. And we're going to call this my private key. We're going to run this through something called a public key generation function, also one way. And we're going to generate a complementary number. We're going to call it my public key, right? So what are the properties of these two numbers? Well, if I have a piece of data, We call it plain text. And I want to protect this while it's being transported to its recipient, right? I can encrypt it, right? We're all familiar with the idea of encryption, where I can encrypt a message and send it. So I can encrypt this using my private key. And I get what we call ciphertext, right? Bunch of gobbledygook over here. The interesting thing about this is that even though I just encrypted it using my private key, I can't actually decrypt this ciphertext and turn it back into plain text using my private key. It can only be decrypted using my public key. And vice versa, right? If I have a piece of plain text and I encrypt it using my public key, well, it can't be decrypted using the public key. It can only be decrypted using the private key, right? So just to summarize that, right, if I have a piece of plain text, I can encrypt it in such a way that only the public key can be used to decrypt it, right? And vice versa, if I encrypt it using my public key, I can encrypt it in such a way that only my private key can decrypt it. Okay, so you might be wondering why this is useful. Well, we're all familiar with, the World War II era, pre-shared key encryption. What's pre-shared key? It's where the sender and the recipient both have some sort of secret password that they both know. And they're using this password to both encrypt and decrypt the data. Right? The challenge comes when the only channel available to me to communicate with the recipient is this single channel where I plan on transmitting the data, right? Because then how do I transmit the password? I mean, think about it. If before every time you visited a website, you had to WhatsApp the owner password or call them up, right? This would very, very quickly become unworkable, right? So, but again, what's the alternative? Given that we are on the internet communicating through these unknown peers, and our messages are being relayed like letters through the post system, through these relays, right? Through these routers. So we use a scheme like this. So Charlie and Alice want to communicate. So Charlie generates a private key. Again, nothing magical here. He picks it out of a hat, and from that, a public key. Alice does the same, right? Picks a number out of a hat, generates a public key. It's a 77-digit number. The odds of guessing it are, again, like winning the lottery 55 times in a row. Now what do? They exchange public keys, right? And now, according to our threat model, right, we're assuming that Dan, Fred, and Evan are eavesdropping on the channel. We can assume that they have copies of these public keys. All right, so now what? So now Alice drafts her message, and she encrypts it using Charlie's public key. Okay, so now that it's encrypted using Charlie's public key, what is the only key in the world that can unlock this message? Charlie's private key. Doesn't matter that Dan, Fred, and Evan have Charlie's public key. They can send messages to Charlie, right? And that opens up a little can of worms that is a little beyond the scope of this discussion. But Charlie is the only one who can decipher this message that is destined for him, right? And when he goes and he replies to Alice, he encrypts messages using Alice's public key, and she decrypts them using her private key. Okay, so now we're going to combine these two concepts. We're going to create something called a digital signature. So let's say you watch this video and you are so taken with cryptography, you decide, I'm throwing everything away, I'm going to become a cryptographer. That's it. You go out, you start applying to jobs, and you walk into a company and they say, well, what's your experience? And you say, I took BJ Dweck's cryptography course, and they say, wow, that's incredible. Can you start tomorrow? And then they say, wait a minute, how do we really know that you took BJ Dweck's cryptography course? So you come back to me, you say, what do we do? I need some proof. So I say, all right, here's what we're going to do. We're going to open up Microsoft Word, and I'm going to type Sam graduated BJ Dweck's cryptography course in September 2017. I'm going to email it to them, stick it on a flash drive, whatever, you bring it over, and you show it to them. And they laugh you out of the office because everybody has a copy of Microsoft Word on their computer, and anybody could have written that, right? So you come back to me, all upset, what are we going to do here? So I say, all right, here's what we're going to do. I'm going to digitally sign this document. You say, well, how do you do that? So I say, okay, I'm going to first take the hash of this Word file, right? Nothing magical here. I'm just running it through this scrambler function, this hash function, and I'm going to get a number, right? I'm going to get its digital fingerprint, this unique number, according to this hash function, SHA-256, that belongs to this file, this document. Then I have my private key, public key pair. I'm going to take my private key and I'm going to encrypt this hash. So now I have a bunch of gobbledygook over here, which is the encrypted hash of this original document, right? And now I'm going to take that gobbledygook and just stick it on the bottom of the Word file such that now I have Sam graduated BJ Dweck's cryptography course in September 2017 with this gobbledygook on the bottom, which we will call my digital signature. Okay, so why is this useful? Well, when you get to the employer, they are going to validate the signature, and they're going to do it like this. So we have the document, right? We understand exactly how this was created, right? We just took the original text, we hashed it, and then I signed it. I encrypted it with my private key, and then we took the results and stuck it on the bottom. So now they're going to remove this digital signature. So now on one side they have the original document, and over there they have the signature that was on the bottom. They're going to take my public key, which everyone has access to, right? No one had access to my private key. They're going to take my public key and they're going to decrypt it. Okay, they get a number, but that doesn't prove anything, right? That doesn't prove anything. They just get this decrypted hash over here. But now they're going to hash the original document and they're going to see that the hashes match. So they're going to conclude that the document has to be valid. Why? Because let's look at a scenario where you tried to make yourself look a little bit more experienced by changing the year, right? You made yourself look one more year experienced. On the way, you took out the flash drive, popped it in your laptop, and opened up the Word document, and above the gobbledygook, you just changed the year to 2016. All right, let's see what happens, right? Now they're going to remove this digital signature. They're going to decrypt it using my public key. Great, okay, they got that original hash. But now they're going to hash the altered document, and they're going to get a very different hash. And they're going to have to conclude that this document, right, this signature that was on the bottom does not attest to this document, right? It may attest to something else, but it doesn't attest to this document, right? And so maybe you followed this 1000%. You could explain it to your friends, but maybe you didn't. The upshot here is if I have a document, if I have a piece of data, I can take my private key, which is a number that I just picked out of a hat at random, and I can digitally sign it in such a way that anyone who has the corresponding public key can then validate that it must have been signed by this private key, right? By the holder of that private key, right? And so now we're prepared to return to our original problem of transaction authorization, right? So let's look at our transaction log. Our transaction log consisted of from account to account amount, right? Obviously, we're not going to use names in this transaction log. We're going to use account numbers, right? This is not a foreign concept at all. We do this in traditional banking. We have account numbers, right? We would expect there to be numbers here. Okay, so if we're going to come up with an account number scheme, right? Numbers are just numbers, right? We can use public keys as account numbers, right? Public keys are numbers after all, right? So we can say, all right, from Alice's public key to Bob's public key 50, right? So from this account number to that account number 50, right? From Charlie to Alice 10, right? And so on, right? This transaction log is just a log of from account number, public keys to account number, public keys, amount. But how does this help us? Well, it helps us in the following way, and I'm going to iterate through this a few times. So let's take, for example, this first transaction where Alice sends Bob $50, 50 units, 50 Bitcoin. So Alice can now take this transaction, she can hash these three pieces of data together, and she can sign it with her private key, right? She can encrypt it with her private key and stick that signature on the end. And what is so interesting, so fascinating about this check now, right? You can think of it as a check, right? A check has a from account, a to account, an amount, and a signature. But what's magical about this check is that anyone in the world can independently now take the from account number, which is actually a public key, and use it to cryptographically verify this signature against the whole transaction, right? That's rather clever, right? We can also do the same to these transactions, right? Charlie, who is the owner of the private key that corresponds to these public keys, can put signatures on the end, right? That could only have been made by the one who possesses the private key corresponding to this account number, right? He's the only one who could have done this. And without knowing Charlie, without knowing anything about him, right, we can cryptographically verify that the account holder signed this transaction. And if any of these pieces of data are altered in any way, it's going to invalidate this signature against this transaction, right? Let's take Dan. Dan has never been seen before by this network of friends, right? His account number, right, his public key is nowhere to be found on this transaction log. Completely new, right? Now he wants to participate. He wants to be found on this transaction log with some units, possessing some units, right? So how does he trade? How does he enter the system? So he generated a private key. How did he do this? He picked a number out of a hat. Very easy, right? Then from that, he generated a public key using a standard algorithm. Now he wants to participate, so he wants to transact with Bob, let's say. Bob holds some units on this transaction log. So he gives his private key. He never gives his private key to anyone. He gives his public key, rather, to Bob. Bob drafts a transaction from Bob's public key to Dan's public key, 20 units. How do we know that Bob had the 20 units to give? Well, we see him further up, right? That Alice sent him 50 units previously, right? So we know he has enough. And now he has this check here that he drafted, and now he digitally signs it using his private key. Now it has a digital signature on the end. Okay, let's look at this one more time within the context of the network, right? This network that we were looking at before, where everyone has their own independent copy of a transaction log, and everyone is a peer, right? No one is, quote unquote, more equal than anyone else. How does this work? So Fred and Bob want to transact. So Fred has his private public key pair, Bob has his private public key pair. Fred sends his public key to Bob. Bob uses Fred's public key to write a check, draft a transaction from Bob's public key to Fred's public key 40. He digitally signs it using his own private key, sticks that signature on the end, and now he has this digitally signed check, digitally signed transaction. He knows it's valid, he knows it's legitimate, so he adds it to his own set of books, his own transaction log. And now he sends it to his nearest neighbor, right? And as he sends it to his nearest neighbor, and his nearest neighbor passes it along, every single node has this transaction incoming. And they're very suspicious, right? This is an environment of no trust, right? So the first thing they ask themselves is, was this authorized, right? And they check the digital signature against the from account number, and they see indeed it was digitally signed, right? And then they ask themselves, well, is there sufficient balance in this account, right? And the answer to that can be found in their own authoritative version of the transaction log, right? They don't have to trust the data that they got from anyone else, right? This is just the product of all the transactions that they've received to date, which everyone else has hopefully received as well. And they can answer that question independently as well, right? And so those are the two central questions at this point, right? Is this transaction valid? Was it authorized? Does it have a valid digital signature, right? That's question number one. And question number two is, does this from account have sufficient balance? And if the answer to those two questions is yes, then we can accept these transactions and we don't have to trust, we have the ability to verify. And that is the solution to problem number one. Now, if that was the end of the story, we would have had these, Bitcoin, these cryptocurrencies, right? We would have had the ability to do this decades ago. because this is decades old technology, right? This is nothing new, digital signatures. And in fact, there were attempts at creating, right? There were precursors to Bitcoin, right? There were attempts at creating digital signature based schemes, currencies. The problem is they all still were centralized. They all still relied on a central party because they could not solve the second two set of problems, right? Consensus on transaction ordering and the creation of units of account. And that's the rest of this story. So let's focus on problem number 2, coming to a consensus on transaction ordering. And this problem is illustrated by the following problem, which is called the double spend problem. And it goes something like this. So Bob has $1 million worth of diamonds, and Alice wants to purchase them. They each have copies of the transaction log that they've been using our methodology, our digital signature scheme to create up until this point, right? And so Bob's first question is, do you in fact have, a million units? Perhaps he wants to know first, right? So Alice says, yeah, sure. Check my public key. So Bob takes Alice's public key, he checks it against his log, and he says, all right, I see that there's $1 million balance on that public key, but prove that you own it, because we both have copies of this log, and we both could just look inside and find a public key that has 1 million units on it, right? I don't know that you could sign for this key, right? And so Alice says, no problem, and she can do that rather easily. She can sign a message that says, hello, Bob, with today's date in it, and she could send it to him, and he can use the public key and validate that signature is legit. And now he knows that she has the ability to sign transactions for this account. So he says, all right, let's do this. So Alice drafts a transaction where she sends 1 million units from her account to Bob's account, and she signs it with her key. Right? And now she passes the transaction to Bob. And now we get to the $1 million question, right? Is Bob confident in handing over the diamonds? Is this transaction considered settled, right? If this was a briefcase full of cash, right, the answer would be yes, right? Because the transaction is settled with possession when it comes to cash, right? There's nothing that the sender of the funds could do to throw a monkey wrench in this transaction once they've handed over the cash, right? Possession is 9/10 of the law, right? But is this transaction a bearer instrument like cash, right? That's the question. It would seem up until this point, right? It would seem superficially that the answer is yes, right? Because Bob could just broadcast this transaction to the network, right? He could pass this along to his nearest peer on the network, and his nearest peer on the network will consult his books and conclude that yes, there is indeed sufficient balance, right? And yes, indeed, this transaction is authorized, and so they'll cash it, right? And so Bob could safely hand over these diamonds, right? Well, no, not so fast, unfortunately. Right? Unfortunately, Alice and Bob are transacting in New York. And unbeknownst to Bob, Alice has an evil cousin who lives in Sydney. And before they met, Alice drafted a second transaction, right? We'll call this the double spend transaction, where she sent 1 million units to a second public key that she controls. How does she have a second public key that she controls? Well, she just picked a second number out of a hat, right? Everyone's free to pick numbers out of hats, as many hats as they want, right? And she just generated a second public key from that second private key. And she sent 1 million units to this second public key, and she drafted this check, and she gave it to her evil cousin in Sydney, and she said, do not send that to your nearest peer on the network. Just hold off. Just hold on to that check. And so as soon as she hands the transaction over to Bob, and Bob gives her the diamonds, she says, all right, go, send the transaction, right? So now you have to consider the fact that on networks, we have what we call latency. There's a propagation delay, right? You can picture this peer-to-peer network as, we're a bunch of, a mob spread out over a football field. And we're all shouting messages that we receive from one neighbor, right? We're shouting them to all of our other neighbors, right? And so you could imagine that it takes time for one message to propagate from one end of the field to the other, right? And so what ends up happening is that if Bob and Alice's evil cousin both broadcast their transactions at the same instant, well, the neighbors of Alice's evil cousin are going to receive her transaction first, right? And the Americas are going to receive Bob's transaction first. They're going to ask themselves, does this have sufficient balance? Yes. Right? Was it digitally signed? Yes. And they're going to cache it, right? They're going to add it to their books, right? And then it's going to propagate even further, right? To Asia, right? And Bob's transaction is going to propagate to Europe and Africa, right? And they're going to cache the transaction. But all of a sudden, we're going to wind up in a situation where the double spend transaction makes it to the Americas and it's going to be rejected. Why? Insufficient funds. These funds have already been spent. They've been sent to Bob's public key, right? And now Bob's transaction is going to arrive in Asia and it's going to be rejected for the same reason, right? These funds have already been spent. They've been sent to the double spend address. And so now we have, in effect, a bifurcated network because we have two different sets of books with two different histories in them, right? And so the question is, how can we solve this problem? How can we come to a consensus on transaction ordering, right? If we go back to the analogy of the mob spread out over the football field, if you're an individual in the middle of that mob, in the middle of the football field, and you receive two messages, right, that originated from opposite ends of this field, how can you possibly know which one happened first, right? How can you know which one originated first? You could say, well, okay, let's add to this scheme this set of rules that we all follow, this set of consensus rules. Let's add a rule that says that we need to timestamp every transaction. Okay, well then people will just monkey with the timestamps, right? Yeah, we just kick the can down the road, right? How do we then verify, right? We need a scheme to verify those timestamps, right? Well, we could say, well, if they look wildly off, then we won't cache them. Well, yeah, but we're dealing on the order of milliseconds here with networks, right? So people could just backdate them, a few seconds, right? I mean, where does that end, right? So that doesn't seem a sufficient solution to the problem, right? Well, perhaps we could then, we could nominate Fred, right? We could say whichever transaction that Fred gets first, right? That's the one that we'll consider, as having been the first transaction, right? Okay, but then, we've centralized this set of books, right? We've given Fred a tremendous amount of responsibility, right? We're no longer all peers in this network. There's someone who's more equal than all of us, right? And so we may as well just throw this entire scheme out the window and call it a day. Right? We can never have any vestige of centralization in the scheme, right? Otherwise, there's just no point. So we can't nominate Fred, right? This problem, was known as in computer science as the Byzantine generals problem because it was framed as 4 Byzantine generals that laid siege to a city, and they had to plan their attack so that they would all attack at the same instant. Right? The problem is the only way that they could communicate was through messengers that they didn't trust. Right? So the question was, how could they possibly coordinate their attack? Right? How could we have this coordination in an environment of no trust? And it was largely thought that there was no solution to this problem. Right? This is the essence of the innovation here. This is the problem that Satoshi Nakamoto solved when he drafted the white paper and when he created this Bitcoin. So what's his solution? What does it look like? Well, we're going to solve this problem with a slight rework. Okay, up until now, what's been happening, right? As from the perspective of a node on the network, from the perspective of Alice, she has been receiving incoming transactions and she's been asking herself the 2 questions. Is it authorized? Does it have sufficient balance? And then what does she do? She adds them directly to her log, directly to her ledger. Well, we're going to change things a little bit, right? We're going to conjecture, right? What if Alice, rather than adding them directly to her log, what if every 10 minutes, right, she was going to collect the transactions that she received and added them to a batch of transactions, right? Just a group of transactions, right? We'll call it a block of transactions, right? And then rather than, right, and then taking this block, she would to enter into a network-wide contest with all the other nodes on the network, with all the other participants in this scheme. And somehow a winner were to be selected at random. And then that block were added to everyone's ledger. And the transactions within that block ordered according to however the node chose to order them, right? Well, then we would have a consensus around the transaction ordering, right? Rather than adding these raw transactions to our ledger, we would add batches that are selected according to a random competition, a random network-wide competition. And so now our story looks something like this, right? Alice no longer has a ledger containing raw transactions. She has a ledger containing blocks of transactions. And as she is receiving transactions from the network and she's validating them, she's adding them to a new block that she's building. And her incentive to be dealing with transactions that perhaps she has nothing to do with, right? Perhaps this is between Bob and Evan, this is between Fred and Charlie, right? As her transaction, her incentive to be participating in this competition, she gets to add a transaction to the top of this block, of this batch of transactions, which is a creation transaction, right? It's a transaction that generates new units of account, and it generates it and awards it to the public key of her choosing. And obviously she's going to choose a public key to which she has the private key, so she can control these new units, right? And so if we zoom out to the network level, right, now our story looks something like this, right? All these nodes on the network, they have ledgers that no longer contain raw transactions, they contain blocks of transactions, right? And we can read through these transactions by going through each block in sequence, and then within each block, going through each transaction in sequence, right? And as transactions are flinging across the network, as Dan is transacting with Charlie, and Evan is transacting with Fred, and Bob is transacting with Alice, right? All the nodes are seeing each other's transactions, and rather than adding them directly to their books, they're collecting them in a block 50 that they are all building. And they are eagerly hoping that they are going to win this network-wide competition. Why? Because the top of the block that they're building contains a creation transaction that awards them with new units of account. So they're hoping that their block 50 is the one that is selected. All of a sudden, Fred notices, hey, I won this network-wide competition. He's very excited, right? So he immediately adds his block to his books, right? And now he passes this block along to Alice. Alice is merrily, collecting transactions in her block 50, hoping to win, when all of a sudden she is rudely interrupted because an incoming block 50 just arrived. And she's very disappointed and she's very suspicious, right? She is disappointed because she wishes that she won the transaction, the contest, right? She's very suspicious because we don't trust anything that comes in on the internet, right? Nothing. We don't trust any transaction. We assume that it's there to trick us, to cheat us out of money, right? And so she immediately sets to work verifying every single transaction for herself. Was it authorized? Does it have sufficient balance? She's perhaps a little disappointed to find, yes, it checks out. Okay, well, let's look at the creation transaction. Perhaps Fred cheated there. Perhaps he awarded himself with more units of account than he's entitled to. Nope, that checks out as well. She's disappointed. Finally, she asks herself, well, perhaps Fred didn't really win this competition. Well, no, she verifies that, and we'll see shortly how she does that. And she's disappointed to find out that Fred won. Okay, now Alice is faced with an interesting sort of choice, right? Because after all, she owns her computer, right? This ledger resides on her hard drive that she owns, and her computer that she bought, that she controls, right? Running a program that she selects, that she uses, right? To do all these things in her stead as her agent, right? And so she can do whatever she wants, right? If she wanted to add her own block 50 to her own ledger, she is perfectly free to do that, right? The problem is that, I have a science textbook on my bookshelf, right? If I want to change chemistry, can I, is it sufficient to just walk up to that chemistry textbook and change a few lines, right? Perhaps no. Perhaps, if I did that, I would be just taking myself out of consensus with the rest of the chemistry community, right? I'd only be fooling myself, right? I'd only be hampering my ability to participate in coherent dialogue about chemistry with other people in the world, right? Because I would have inconsistent data in my textbook, right? So much the same way, right? If Alice just chose to add her block 50 to her own ledger, right, she would be shutting herself out of the network. She wouldn't be able to participate in this collective endeavor of maintaining these books, right? And so she's forced to add Fred's block 50 to her books and work on 51 and pass it along. And so that's what she does, and her neighbors, make the same calculation and do the same thing. Okay, so now you might be wondering, how can we have such a contest, right? Who determines the rules of this contest? How do we make sure that that the winner is indeed selected at random, right? Haven't we kicked the can down the road, right? Because it would seem here we have to certainly rely on Fred, right? There must be someone who is determining the rules, determining the winner, right? But no, right? We can't rely on Fred. Again, we have to come up with some way to not rely on Fred. Otherwise, we have to throw our entire innovation out the window. And so the answer as to what is the nature of this contest, comes back to our trusty old hash function. Okay, only now we're going to consider just the first digit of the hash function, right? How many possibilities are there for this first digit? There are 10, right? It can be anything from 0 to 9 inclusive, right? So we have 10 possibilities for the first digit of this hash, of the output of this hash function. And so now I'm going to give you a problem. Find x where the hash of x comes out to a number that starts with a digit that is less than 3, right? So what's your plan of attack, right? You have to throw something in that the resulting hash starts with a digit that's less than 3, right? It has to start with a 0, a 1, or a 2, right? So you might, first instinctively just think, all right, so I'm going to take a hash that starts with a 1, and I'm going to run it backwards and see, find something that I could throw in. I'm going to look at that, Wikipedia, SHA-256, I'm going to look at the procedure and I'll figure it out. Nope, that's not going to work. You can't run it backwards. It just doesn't work. All right, so, what tools do you have left? You basically have to use trial and error, or, what we call in computer science a brute force algorithm, right? You have to try every possibility. It's the most difficult, obviously, kind of algorithm to solve in computer science. So you throw in a tulip, you get something that starts with a 7, you throw in an apple, you get something that starts with a 4, right? And you're just randomly throwing in objects. And all of a sudden, you throw in a cactus and you get a hash that starts with a 2, and you say, great, I won, right? What percentage of the time are you going to win this game? Well, the output of a hash function is uniform, right? I have an equal probability of getting any hash. And so if that's the case, then I'm going to expect to win this game 30% of the time, right? 30% of the things that I throw into this hash function are going to hash to a hash that starts with a digit that is less than 3, right? I'm going to get a 0, a 1, or a 2. Well, let's say I change the rules of the game now, and I tell you, find me x such that if I throw it in, I get a number that starts with a digit less than 2. Have I made the game easier, or have I made the game harder? Right? I've made the game a little bit harder, right? Now you're only going to win 20% of the time, right? And so with that in mind, right, what's the nature of this contest? What is each node doing when they are building this new block? Well, they are doing the following, right? They have a block, and at the top of the block, there's a label. We'll call it a header. And much like a mailing an envelope label, it has different fields that you can enter information. Right? There's a field for a last block, right? And there's something called a nonce. And I'll explain that in a moment. And as transactions are coming in from the network, right, totally unrelated to the node that is actually building this block, perhaps, right, in all likelihood, right, this node is adding those transactions to their block. And of course, they have the creation transaction at top, right? It's called a Coinbase transaction, actually, not to be confused with the exchange that took its name from this concept. And they have a problem to solve. What's the problem that they have to solve? Hash this block such that you get a number that is less than 1 kabillion, right? Some big number over there, right? It's a very big number, but look at all those leading zeros, right? It's not the full 77 digits of the output of this function, right? There's a lot of leading zeros. It's only a fraction of the range of the full extent of the output of this hash function. Okay, and so now they have this block. They have all the transactions they've collected. They have the creation transaction. They have some labels at the top, and they hash the block. And they get, unfortunately, they don't get less than 1 kabillion. They get this larger number here. Okay, so now they're a little bit stuck, right? Because if I hash this block again, I'm just going to get the same number. I need to modify this block in some way. And so that's what the nonce is for, right? Because this nonce can contain any number. So they'll stick a 2 in the nonce, and they'll get a different number, right? Just by slightly modifying this block, I can get a completely different hash, right? And so they keep changing the nonce and hashing, and changing the nonce and hashing. And all of a sudden, they get this number. Look, it's less than 1 kabillion, right? Still a very big number, right? But it's less than the full range, right? And this presumably took them a while to do, because it's sufficiently hard to get less than 1 kabillion, right? And so if we zoom back out to the perspective of the network, right, it looks something like this, right? All the nodes have this ledger, have their set of books, right, with blocks in them from 0 to 49, and they're all working on block 50. They're all collecting transactions and hashing and changing the nonce and hashing and changing the nonce and hashing and hashing. All of a sudden, Fred sees, wow, I hashed my block and I got less than 1 kabillion. He's very happy, right? He won. He adds his block 50. He passes it along to Alice. Alice, as we said, is very disappointed and extremely suspicious. She verifies every single transaction in this block. She verifies the creation transaction. And then finally she says to herself, wait a minute, did Fred actually win this contest? How does she verify that Fred won the contest? Simple. She hashes the block. How many times? Once. Takes a second, right? Not even. I mean, it takes like a millisecond. And she, even less. And she hashes this block and she verifies that Fred indeed won this contest, right? It's sort of like a jigsaw puzzle, right? A million-piece jigsaw puzzle. If you see it assembled, you know it took someone a very long time to complete that puzzle. And you can verify that it's done correctly in an instant with a glance, right? You can tell if there's a missing puzzle piece right away. It jumps out at you, right? So it's similar to that, right? And so Alice now is faced with the decision, does she fool herself by adding her own block 50 to her ledger, or does she add Fred's, right? And she begrudgingly perhaps adds Fred's block to her ledger, and she starts working on block 51, hoping that perhaps next time she'll be the one to hash a block to less than 1 kabillion first, right? And she passes it along and so on. And so with that, we've solved the problem of transaction authorization, and we've solved the problem of consensus on transaction ordering, right? How do we achieve that? And we've also solved the problem of creation of units of account. And so we now just have a few smaller items around this to discuss. The first of which is the difficulty adjustment, right? In other words, how do we get this 1 kabillion number? And wouldn't we want that number to change over time? Well, first of all, why do we want this number to change over time? Well, we want that because, as you could imagine, consider the first few moments after Satoshi Nakamoto launched block 0 in the blockchain in 2009, right? Presumably, he was the only one participating in this competition with his laptop, and he was trying to hash these blocks every 10 minutes, right? But very soon, other participants joined the picture and started hashing blocks and participating in this contest as well. And so you would expect that the rate of blocks coming in would have increased, right? They would have come in more rapidly, right? And this is something we don't want, because as more and more we call hash power joins the network, right, blocks would come in more rapidly. And pretty soon we'd have just these empty blocks with no transactions in them, because there wouldn't be enough time for them to fill up, right? And so we want to sort of maintain this steady heartbeat of blocks coming in at a rate of every 10 minutes on the average, right? So how can we adjust this number, right? So we could nominate Fred, right? We could say, all right, Fred can sort of decide what's the number, and he can take measurements of the network, and right? But again, right, we would have to throw the entire innovation out if we relied on Fred. We have to come up with some way where every man is his own island here, right? Where everyone can just independently, based on their own books, on their own calculations, arrive at the same conclusion, right? That is the nature of this. It's a very different kind of engineering problem than software engineers are accustomed to. And so we wind up with a calculation like this, which is if we want blocks to come in at 10 minutes at a rate of, one block every 10 minutes, if we do the arithmetic out, we find that in a 2-week period, we should wind up with 2016 blocks, right? Nothing magical about that. It's just arithmetic. And so every 2 weeks, right, roughly, right, the picture looks something like this from the perspective of a node. They're gathering blocks on their ledger, right, and they're keeping track of every time 2016 blocks come in. So you receive block number 22,176, and Alice says, oh, look at that. It's been another 2016 blocks. Well, this period that it took to accumulate from blocks 20,160 to block 22,176, right, that period of time, right, it should have taken 2 weeks, ideally, right, if those blocks were coming in a block every 10 minutes, right? And so the question is, did it take longer than 2 weeks? Well, if it took longer than 2 weeks, right, well, then it's too hard, right? We have to raise the 1 kabillion number. We have to make it a little bit easier to win this contest, right? And conversely, right? Did it take less than 2 weeks, right? Maybe it was too easy, right? Maybe too many more people joined this contest, right? And so we have to make it harder, right? We have to lower that 1 kabillion number. And so every 2016 blocks, which hopefully happens, roughly every 2 weeks, every node is asking itself this question, and then doing the exact math, the exact division to find out what would have been the ideal number, right? Such that this would have taken exactly 2 weeks. And that's the number they use as their new 1 kabillion number, right? Independently, they all arrive at the same answer. Okay, so that's called the difficulty adjustment. Happens every 2016 blocks, right? There's another question, right? Why not mine empty blocks, right? If you think about it, why do these nodes on the network, right? Alice, Fred, Dan, right? Why do they bother accumulating any transactions at all in their blocks? Why not just hash these empty blocks, right? And they'll win just the same, right? So as an incentive, what we do is we have a rule that nodes on the network, when they are transacting with one another, they have the possibility of including a fee, right? This fee incentivizes miners, right? Those are looking to mine blocks, to hash these blocks. It incentivizes them to include their transaction in the block, right? And I don't want to spend too much time on this, these transaction fees. I discussed this at length in a later part of the presentation, but I think it's important to note this here. Actually, I showed this presentation to Giacomo Zucco, and fantastic, brilliant mind in the space, and he felt it was very important to include a note on this here. So there's something called a transaction fee that you can include along with your transaction that incentivizes these miners to include your transactions in the blocks. And they're able to collect those transactions along with their those transaction fees along with their block reward. Another question is, what's the rule that governs how much each block is allowed, how much each miner is allowed to award themselves at the top of each block with that creation transaction? And so Satoshi Nakamoto built in the following rule, which is that the block reward shall be 50 units. But every 210,000 blocks, which is roughly every 4 years, right, that reward shall halve. So it started at 50 units, it halved to 25, subsequently halved again to 12.5, and subsequently, several months ago, halved again to 6.25, where we are at now. This trend will continue, until we get to a little bit less than 21 million units that will ever be created from these creation transactions. And then there will be no more created. There will only ever be 21 million some odd Bitcoin. The last problem that we need to consider here is around something called chain splits, right? It would seem, that yes, we've solved the problem of what happens when two nodes on the network broadcast a transaction at the same instant, right? How we avoid a double spend and how we can come to a consensus on transaction ordering. But it would seem, perhaps we kick the can down the road, right? Because what happens if two nodes on the network solve a block at the same time, right? They're able to hash a block such that it comes out to less than 1 kabillion at the same time, same instant. So let's examine that situation. Let's see what happens in that case. So what if a node in New York and a node in Sydney mine a block at the same instant? All right, so I think this is best understood from the perspective again of a node, right? Let's look at it from the perspective of Alice, right? So Alice has blocks 0 to 49 on her ledger, and she is working on 50. She is accumulating transactions as they come in from the wire. She is validating them, and she's adding them to block 50, and she's hashing. Unbeknownst to her, at this instant now, a node in New York and a node in Sydney have both mined a block. But, right, as we saw before, some nodes will find themselves closer in terms of latency to New York, and some will find themselves closer to Sydney. So Alice happens to be closer to New York, and all of a sudden she receives 50 New York. She says, oh, rats, I wish I won, but I didn't. And so she adds 50 to her ledger, and she starts working on 51. But you'll notice, not just any 51 and not just any 50, right? She's adding 50 New York to her ledger, and she's mining on top of 50 New York. So this is a 51 New York. Why? What enforces this? Well, if you'll recall, before we saw that there are labels on top of each block, right? There's a block header, and that header contains fields, right? It contains the number of the last block, it contains the nonce, right? And it also contains the hash of the previous block. So the block that Alice is working on, this 51, contains in it the hash of block 50, not any block 50, block 50 New York, specifically block 50 New York, right? This block 50 New York is unique, right? If only because it has a Coinbase transaction on top that belongs to the one who mined it, right? So it's going to be different than any other block 50, the block 50 that's mined in Sydney, for example. So Alice's 51 is inextricably linked to 50, to 50 New York, the one that she's mining on top of. You would say this inextricable link creates a chain, or a chain of blocks, or a block chain, right? And so Alice is mining 51 New York, right? An instant later, she receives 50 Sydney. She says, oh, that's interesting. And she adds it to her ledger, and she has what we call a chain split. But she received 50 New York first, so she continues to mine on top of 50 of her 51 on top of 50 New York. And similarly, the nodes that are closer to Sydney, they're mining 51 Sydney. And as unlikely as it is that two nodes on the network will mine a block at the same, instant roughly, though it does happen, it's even less likely that that would happen 2 times in a row, right? And so we would expect that of the groups that are mining, right, the group closer to New York that is mining 51 New York, and the group closer to Sydney that is mining 51 Sydney, we would expect that one of those groups would win far before the other. And so Alice, for example, could receive, oh, look at that, 51 Sydney, right? She add that to her books. And now she throws away 50 New York and 51 New York. Why? Because of the following rule. Every node shall mine on top of the longest chain that they have. If we add that rule to the set of rules that we all follow, what we call the set of consensus rules, right? Then the entire network will converge on the same chain. If we're always mining on top of the longest chain, right? The network will converge on a single chain, because as unlikely as it is to mine a block at the same time, though it does happen, it is less likely that will happen 2 times in a row, right? And perhaps, that is highly unlikely, though still within the realm of possibility. It is far less likely that will happen 3 times in a row, right? And so on and so on. And so we can expect to converge on a single chain if we all mine on top of the longest chain. Now, incidentally, you might be wondering, well, what happened to those transactions that were contained in 50 New York, right? Those poor guys, right? They were chucked off the chain. Well, usually, right, a lot of those transactions, there's probably a lot of overlap between 50 Sydney and 50 New York, right? Most of the transactions that 50 New York contained, probably 50 Sydney contained them as well. But those that weren't, and certainly there were some, they're returned to Alice's pool of transactions that she is looking to include in blocks, right? And each nodes as well. We call this the mempool, as if there is some centralized pool out there. But in fact, there isn't a mempool, right? That can't exist, because otherwise it wouldn't be decentralized. And every node sort of just returns those transactions to their pool of transactions to be included in later blocks. And so finally, this brings us back to the last question in this last technical slide. When does Bob finally hand over these diamonds and consider this transaction settled, right? So let's examine this, right? Bob has his transaction in hand. He has a copy of this ledger from 0 to 49, and he broadcasts it to the network. Does Bob now consider this transaction settled? Does he hand over the diamonds? Well, based on everything we've seen, that would probably not be wise, because he could be the victim of a double spend attack, right? Alice could have her cousin broadcast the transaction, and it could be included in block 50, and perhaps Bob's wouldn't, and that would be that. So we say here Bob has 0 confirmations. Perhaps it's prudent for him to wait until it's been picked up in a block 50, right? Then he has 1 confirmation, right? Perhaps then, he could be excited and say, that's it, I'm in a block. Everyone, has confirmation that my transaction came first. I'll hand over the diamonds. Well, okay, he could say that, but perhaps that's not prudent, because it could be that there's a chain split, right? It could be that, in another moment, there could be another block 50, and then mined on top of that a 51, right? And his 50 could be knocked off, right? We call such a situation a reorg, right? That stands for a reorganization. It's a reorganization of the chain, right? So his transaction could be reorged off the chain. So perhaps he wants to wait until 51 is mined on top of the block, and he has what we call 2 confirmations, right? Or perhaps he'd want to be more prudent and wait for 3, right? We said that blocks come in every 10 minutes, so perhaps this is about a half an hour. And so at a certain point, we have enough blocks mined on top of his blocks that he can feel fairly confident that there isn't enough computing power on the planet to be able to very quickly, within a minute or so, mine 1, 2, 3, 4, 5, 6 blocks on top of 49 in order to reorg all these blocks off the chain, right? He has 5 confirmations, and so he could feel confident in handing over the diamonds. As a matter of practicality, this becomes largely subjective, right? The answer to this is largely subjective. It becomes, what is the value of my transaction, right? Perhaps if I am a vendor selling someone a candy bar, I will be content to just accept a 0 confirmation transaction, right? Perhaps, I accept, credit card chargeback risk every day as the cost of doing business, right? Because when I accept that credit card for the candy bar, I don't get my money for 6 weeks. And if it was fraudulent, then my account gets charged $20. So, but I accept it anyway, right? And so perhaps for the cost of the candy bar, I wouldn't mind just handing the guy the candy bar. But for a larger value transaction of diamonds, perhaps I would insist on, 5 or 6 confirmations, just as a noteworthy matter. I guess in the earlier days of Bitcoin exchanges, we're insisting on about 6 confirmations. Nowadays, it's about 3. So that's largely accepted as being safe. So, that concludes really the technical part of this presentation. And just to conclude, you might be wondering, right? Why did I just sit through that, right? Why was all that necessary? Cars are very useful devices. I don't have to understand how a car engine works in order to use it, to understand its value proposition. Why is Bitcoin different? Why was that important? I think it's important for a few reasons. So, when we're presented with a new, investment opportunity, a new asset, we're suspicious, right? And rightfully so, right? We should be suspicious. We should vet these things. We have concerns. But I think, in general, those concerns fall into two buckets, right? One concern is, where did this asset originate? And, who am I trusting by investing in this asset, right? Who is the CEO of this company? What are their promises worth? What does their balance sheet look like, right? And then the second bucket of concerns is around value. Okay, so fine, I trust these people, but how do I know that the value is not going to go to zero, right? And so I think that it's very useful to have this technical understanding of where Bitcoin came from and what it's about, because it very much addresses that first bucket. Who am I trusting, right? The answer is this was built from the ground up, right, to facilitate verification rather than trust, right? There is no CEO of Bitcoin, right? That's a very difficult thing to convey to someone who thinks that they're entrusting their savings now with some, weird cabal of hackers, and they're wondering, well, can't this guy print more, right? It's very difficult to convey the answer to that without really going through these technicals and seeing the bottom line, which in my mind is, we can't rely on Fred, right? Everywhere where we could have said, all right, let's rely on Fred, right? We ruthlessly tried to eliminate that at great expense, right? At the expense of making the system, very complicated, like a Rube Goldberg machine, right? We ruthlessly eliminated every single time that we would have had to rely on Fred, and we created this contraption here that works. And so, I think it's important to understand that this was designed from the ground up to put you in the driver's seat and to create this asset for you as a means of self-sovereignty. And not only did we eliminate reliance on Fred, but we're not even relying on Satoshi Nakamoto himself. In fact, the moment that Satoshi Nakamoto launched this into the wild, he no longer had any more control than you or I, right? So in a sense, we're used to having things that are man-made and controlled by man, by some individual, and we're used to being subjected to certain laws of nature that are immutable and static and unchangeable by any individual. And in a sense, this is really the first innovation that can be viewed as sort of a man-made law of nature, right? Satoshi Nakamoto cannot violate any of these consensus rules. So I think that that's something that really can't be appreciated unless we're stepping through these technicals. In addition to that, I feel that, there's a tremendous amount of skepticism to the space in general, and there should be, right? Because, there are a lot of scams out there, and there are a lot of, with this great innovation, definitely came a lot of scammers riding on its coattails. So we really have to vet everything, and with that comes a sense that there's just really a lot of hype and hot air about nothing. So I think that the technicals are also instructive, just to give you a peek under the hood, and show you that there is a real innovation here. So I think for those two reasons, I think that this kind of a discussion is indispensable. And I thank you very much for your time. I do give a part two where I talk about my thoughts on blockchain, my thoughts on Bitcoin's value proposition, my thoughts on mining economics, Bitcoin as an investment, and privately, professionally, I design custody solutions for people to hold and store their Bitcoin in a safe way. In a way that makes them self-sovereign and puts them in the driver's seat with respect to the Bitcoin, and protects them security-wise at the same time. And I design self-sovereign technology solutions, such as imagine a Google Drive or a Dropbox that that sits on your own hardware that you control. That you don't have files sitting in Amazon data centers. So that's just a note about me. But thanks again for your time. I hope you enjoyed.